All right, so the non-basic variables are variables that are assigned a value of zero. So if they have a zero, they're non-basic. And if they're basic variables, it's going to be anything else, anything that has a number. So those are going to be our basic ones. Now, row six from our previous example, which is the one where we had the max, we had a six, a four, a zero, and a zero. So our basic variables in this case were the six and the four. And our non-basic variables were the zero, zero. So S1 and S2 were non-basic, X1, X2 were basic. And so that's how we can read those. So when they start talking about what are your non-basic variables, and what are your basic variables? Basically, the basic ones are numbered, the non-basic are your zeros that are assigned. Okay, so that's kind of just terminology that you kind of need to have for this. All right, now what if we have k decision variables instead of two? Because remember, the last time we had two decision variables. Now we can have k decision variables. Now, assume that a standard maximization problem in standard form has k decision variables, so x1 through xk, and m problem constraints. Now, we can use select variables s1 through sm to convert the I system to an E system. That's not a problem. And then we're going to form a table with, now what we're going to do is we're going to use combinations. It's going to be k plus m, c, and then k. So that's going to be k plus m columns. And so, our columns are going to be labeled x1, x2, x3, all the way to xk. And our select variables after that, s1 through sm. And now our first row, we're going to go 0 to the x1 and x2, and then 0 to x1 and x3, and then 0 to x1 and x4, and so on until we get all our double zeros done. And then we're going to complete each row in the solution just like we did before. So we're basically going to do this. So the more variables out this direction and the more rows you have, the more you have to calculate and do by hand. This one we had to do only, 6 calculations. The bigger it is, the more calculations you're going to have to do basically. And again, we're going to find the max value P over those completed rows that have no negative values over the basic feasible solutions. And that's going to be only if the optimal value does exist. Sometimes you won't find anything, and that's because it probably initially, if we had something, it might have been something that was like this, and it was maybe unbounded or something. It was something weird, or it had some weird values and it had a lot of negatives or something like that. So that's going to be what we have to do. And so one thing, benefit of this table is it gives a way to find all the corner points. And that's what we've done. If we would actually have plotted our equations back here and put X's and Y's and stuff like that, we would have found our, corner point here, 0, 0, and then we have a 0, 8, a 0, 12, a 12, 0, a 9, 0, and a 6, 4. We would have had all those endpoints. So that would be helpful. We wouldn't have to draw the graphs. But this actually becomes impractical if the number of decision variables and problem constraints is large. So if k decision variables and m problem constraints is found with, say, k equals 30 and m is 35, then we're going to get 65C30, and that's going to be, and somehow my 18 went down, it's 3 times 10 to the 18th rows, which means we have to find a new way to do this because I'm not going to go through that many rows to calculate that many variables and go through that because that's even with 6, it took a long time. If we had 10 to the 18th, doesn't matter if that 3 is out in front or not, that's a lot of rows. Okay. So we're not going to do that. So what I'm going to do is I'm going to stop there and then I'm going to do one last problem here.